So here's where we left off yesterday. We didn't have time because it was a shorter class, but we left off. We had done a couple of problems where we ran through an entire hypothesis test. We did that. We'll run through some more today, so I won't remind you of them just yet. Hopefully you remember the process we did. In those examples yesterday, we had reason to believe that the alternative hypothesis should be either greater than or less than. So just as a reminder, one of the scenarios was the basketball player claimed to shoot 85%. We tested it. We said we couldn't reject the null hypothesis, but we did suspect that she shot less than 85%. So we had a null hypothesis that was the true proportion is 85%. And the alternative was that the true proportion was less. Oops, I put equals. What a silly thing to do. Less than 0.85. So we tested one direction on this. Then we had another scenario that was have the rates of abnormalities increased, and we're not saying because of chemicals, but has the rate of it increased. So the null hypothesis is that no, it hasn't increased, and the proportion is still 0.05. The null was that it has increased, and so now it's, see, I keep doing that, is greater than 0.05. Those are what we call one-tailed tests because we're only testing in one direction, greater than or less than. Okay, so there you go, one-tailed test. And the tail comes from this, right? We have the sampling distribution that we're testing with our second example. Remember, it was like a huge, like 6.27 z-score way up here. We're only testing this part of it right here. That's technically our test statistic. And we're only testing that area right there, which is the p-value. We don't care about values below. Okay, and we'll show what that means because there we go. It's only one of the tails, in this case greater than. We might run into a problem where we aren't so sure if the alternative should be one way or the other. So maybe in this case, our alternate hypothesis, if the null is that the true proportion is 0.35, whatever, I'm making something up, then the alternative, maybe we don't say it's greater than or less than, we just say, I don't think that was correct. So we say it's not equal to 0.35. We're not saying it's greater than or less than, we're just saying it's not 0.35. And this is something, now why would we check not equal to instead of greater than or less than? Sometimes it's very obvious. We're only interested if something is greater than or less than. But sometimes maybe we just don't think this number is accurate. I don't know what the real number is. I don't know if it's bigger or lower, but I really don't trust that number. So I want to test to see if it's not 0.35. All right, and here's an example. Maybe you think this was some biased sampling. So now you can look at that and you can test the hypothesis. So there it is. A two-tailed test means we're testing both directions of change. And the only difference between a one-tailed and two-tailed test is that we will need to double the calculated p-value for a two-tailed test. If the doubled p-value is still below the significance level, we can determine that there's a statistically significant difference that can't be explained by random chance. So it's a very straightforward idea behind mathematically what we have to do if it's two-tailed. So what we're saying, just to put a diagram on this, let's say that with a one-tailed test, we're only testing this side. A two-tailed test doesn't mean we're getting all this area here. That's not what we're testing. We're saying if there's a z-score, I keep saying z, but let me make sure it's really clear. This is the test statistic. If I've got a test statistic right here, then I don't know if this true test statistic should be at the high end or the low end. So I'm going to copy it over here. And essentially, I'm taking this p-value right here, and I'm doubling it because I'm also going to get this area under the curve, and that becomes the p-value. So this is just, I can just say 2 times the p-value for a two-tailed test. Really, really straightforward. So the only thing that's tricky about this is deciding when we should use not equals to instead of greater than or less than. And this we can find in the question prompt. If it explicitly states there's a difference in one direction, we can just do the greater than or less than. It did explicitly say in that last problem with the chemicals, it was saying they think that there's been an increase. So for testing an increase, we say that the true proportion is now greater than what was claimed. All right, if the question simply states that the value is different, not the same, or that the null value is not accurate, or anything like that, if it doesn't give us a clear direction which way we're testing, then we can say it's going to be, okay, instead of saying P is greater than, 0.35, let's just say, I'm not sure if it's supposed to be greater than or less than, so not equals to. No. So if you're not sure, use the two-tailed test. It's going to be more conservative. Imagine you get a p-value of 0.04 with a one-tailed test, and now you have to double it. So you get 0.08. With a two-tailed test, it's no longer statistically significant. With a one-tailed test, it would be. If you know it's a one-tailed test, that's great. Just stick with it. But if you're not sure, go more conservative, and then you can fail to reject the null, being more conservative here. Okay, yeah, nothing changes until the very end. You set up your hypotheses at the beginning, you run through the full thing, and then at the very end, you double the p-value, and then you do your conclusion based on that. So here we go. Let's just do one example of this, and then we're going to move on to the next content. All right, so the National Center for Education Statistics monitors many aspects of elementary and secondary education nationwide. Their 1996 numbers are often used as a baseline to assess changes. In 1996, 31% of students reported that their mothers had graduated from college. In 2000, responses from 8,368 students found that this figure had grown to 32%. Is this evidence of a change in education level among mothers? Well, this is not asking, even though we can see that the number has increased, it's not saying, is this evidence of an increase? It's saying, is this evidence of a change? And to be more conservative, let's go ahead and set up our null hypothesis to be that this proportion hasn't changed. So what would my null hypothesis proportion be? There it is, 0.31, because this is the baseline that we're measuring against. Now we want to see, has it, well, increased or decreased? And it's a little bit counterintuitive, but basically, is there a change? So what, well, yeah, at that point, just to be on the conservative side, we'll say, well, it's not 0.31 anymore. All right, and now at this point, we need to go through the process again. We want to do a one sample z-test for proportion. We can check our conditions. That's what I was trying to find. I'm going to be a little bit lazy on this. Random, 10%, and normal. All right. Is this random? Yeah, we have reason to believe that in a study, it would be random. So rather than writing out a sentence, I'm putting a check mark. If I was submitting this for AP readers, I would definitely write out a sentence explaining my thought process, but I'm lazy. Okay, 10%, 8,368 students. Is that less than 10% of the population? Yeah. Yeah, I think there's more than 84,000 students. So yes, it's 10%, but again, Write a sentence to that effect. And lastly, normal. How do we assess normality for this?
So you gotta do P times N and then 1 minus P times N. See if it's greater than or equal to 10.
All right. And remember for this, we use P sub naught, the null proportion, not the sample proportion. All right. So that's going to be 8,368 times 0.31. And then that gives us 8,368 times 0.69. And spoilers, that's definitely going to be 10. All right. We can calculate, we can get the numbers, but I'm going to go ahead and put a check mark there. We know that's going to be more than 10 successes and 10 failures. Okay. So with this, we know it's random. It's going to be an unbiased estimator. It's 10%. We can use our basic calculations rather than more complex calculations. And normal, which means we can use normal CDF. Okay, now we've checked. Now let's actually perform the test. And remember, I want to start by putting the generic formula. My test statistic, and I say it every time, but I'll say it here. This comes straight from the AP formula sheet. The test statistic is equal to the stat minus the parameter divided by the standard error. My specifics for this formula, I'm finding a Z test statistic. The stat is 0.32. The parameter is 0.31. And maybe I'll pause right there to make sure that you know where these numbers are coming from. Are there questions on why I put 0.32 minus 0.31? Okay. Yeah. Okay. So we can see that we can actually see those numbers here, but it's important to know that this is the baseline we're comparing it against. We want to see if it's changed from there. And this is now our p hat to say that this is the change that we're testing. Okay, now we can do the standard error, which will be p sub naught. Oh, I'm an idiot. Not really. Kinda. Sometimes I am. But I started plugging numbers in. I didn't want to do that right away. It's going to be p hat minus p sub naught. And here I just wanted to put in the symbols, the notation. I didn't want to plug in the numbers yet. Now I can plug in the numbers. So now it's going to be the 0.32 minus 0.31. I didn't give myself a lot of room here, but I'll see if I can squeeze this in.
So where do you double the P?
That's going to be at the very end. All right, double the P value. Yeah, and that's the problem with stats. So many things are used for P. R is reserved for your correlation coefficient, but you also see it used in other places randomly. So anyways, P gets to be a number that's overused. So you have to remember P value and P hat, P sub naught, P for population proportion. Those all mean different things in their proper context. No, and no, I understand that you got it. I just wanted to say that because it's worth pointing out that stats can be pretty confusing on that front. All right, now it's divided by the sample size. What is our sample size here? 8,368. Now here's one thing that I didn't really make room for. I mean, I have room for it, but I didn't really do this. Maybe at the same time that you come up with your hypotheses, this is something I skipped over. What should our alpha level be here? Let's go with 0.05. They don't tell us to use anything different. It's also a good idea maybe to write out your p hat, your p sub naught, and your sample size up here, just all at the top, so it's very clear what numbers you're using. All right, because at the very least, if someone grading your test can trace this back to, oh, they used the wrong p hat, and that's why they got the wrong answer, they can see it up at the top. Oh, there was their mistake. But anyways, p hat is 0.31. 0.32. P sub naught is 0.31. N was 8,368. So this is kind of after the fact I'm adding this, but it's still good to show it. Now we can go through, you can do the math, and I will just leave this here as an equal sign, and someone can fill that in with the test statistic. So 1.978, that's exactly what I got. That looks good to me. So this is where we want to draw a diagram. And, you know, really only at this point do you need to care about drawing a diagram. But what we've got is a presumed mean of this sampling distribution of 0.31. We've got 1.978, which is essentially about right here, maybe, is my test statistic. .978. And I want to test this, but because it's not equal to, I also am testing this area down here. So p-value and p-value. Now we only calculate one of them, and then we just double it. So this is where the doubling happens, and we can do, because we've checked all of our conditions, it's just a normal CDF. And we can show that this right here, not only is it our test statistic, this is where the 0.32 is. Anyways, normal CDF, I'm not going to put in all the parameters, though that's a good idea to do so, and label where the numbers come from. So maybe to be less lazy, I'll go from 1.978 to infinity with a normalized standard or a standardized normal model. So there we go. And what did you get? Just not all at once, guys.
My calculator again.
Does anyone in the room have a calculator today? Well, that will be handy to have. Okay, now it's now it's turned into Cyrillic. All right. So that is 0.0239, and that would round to 0.0240, but we're good. So this is the p-value if it was a one-tailed test. Now we just need to take this and double it. There we go. Now we've done a two-tailed test. How hard was that? So this essentially becomes well, wait, actually it could be 0.0239 based on what you rounded. So it's all in the same ballpark. So for me, the way I rounded it, it becomes 0.0479. If you're off by some, it's not going to be off by much. I know that much. All right. So yeah, as long as you're right about that. So is this a statistically significant result?
Yes, because both of them are less than 0.05.
There you go. Our combined p-value is less than 0.05. There's a less than 1 in 20 chance that this would happen by randomness. So therefore we say that maybe there is something going on. And just to wrap this up, I will maybe I will erase this and just use this open space to write my conclusion. Now keep in mind, on a FRQ on the test, they're going to give you plenty of space, plenty of blank space to write this stuff out. So you're not going to be pressed for space like you are on a screen. But anyways, here's where I could say, because that doesn't look like any English word at all. Because the p-value is less than alpha, here's what I'll say 0.0479 is less than 0.05. We reject the null hypothesis. there is convincing evidence.
You must say there's convincing evidence something supports on the
As long as you have the context. But if you just say something is afoot, no. There's convincing evidence that the education, I'm going to put ... right here. The education, where does it have it in? There it is. Change in education level among mothers. So I'm actually just going to pull this from the prompt, that the education level among mothers has changed. All right, and of course, the last question now is, do you think this difference is meaningful? It's statistically significant, which is not the same thing as being meaningful. What do you guys think?
I got sidetracked looking. I don't think I don't know. I didn't hear your question.
What did it move from and to? Yeah, is that a meaningful difference? I mean, it's movement up. If we want mothers to have higher education levels, and I hope we do, then that's good. That's moving upward, not down. But is it that different? Probably not. But statistically significant. All right, I'm going to skip over any other these types of problems, but there are, I think I have some more practice problems here. Oh, I got a lot. But we're going to skip over those because I wanted to get to today's lesson. And this is statistics story time. Okay, it's going to be a little bit choppy in your video, but we are literally going to watch this video. I'm not going to record it though. So we just saw the story of the boy who cried wolf. Why did we watch that? Because it relates to statistics. It relates to one of the, I don't want to say, well, it is a somewhat difficult concept because it can take a little bit of like wrapping your head around the question and trying to figure out which error is applying in which situation. And there's no, I think by relating this to the boy who cried wolf, we can remember the type 1 and type 2 errors. But without this, it's a little bit hard to remember which error means what. So let's run through this. In the story, the boy cried wolf and the townspeople came, not realizing it was a trick. We're going to turn this into statistical language. We could have a null hypothesis. The null is that there's no wolf, right? Because there's normally not a wolf. So there's no change. The alternative is that there is a wolf. So at the beginning, when the people came, they rejected the null hypothesis, thinking there was convincing evidence to do so, right? So they had a p-value below 0.05. They decided to reject the null, and they thought there was a wolf. There really wasn't a wolf. It was a trick. This is a type 1 error called a false positive. Okay, so this, remember, this happened first. They rejected the null incorrectly, and that's a type 1 error. So it happened first, so it's type 1. All right. And of course, remember, if you're trying to take notes on any of this stuff, the presentation is on today's class page. So the boy cried wolf when later in the story, the boy cried wolf when there was one, but the townspeople didn't come. And so we're looking at this from the townspeople's perspective. There is a wolf, there is no wolf as the null, there is a wolf as the alternative. And when they stayed at home, they failed to reject the null hypothesis, not finding convincing evidence to do so. Their p-value was higher than their significance level. They failed to reject the null hypothesis incorrectly. And this happened second. So this is a type 2 error. And honestly, I do use that mnemonic in my head. And so I think, okay, they rejected the null when they shouldn't have. That was first, therefore it's a type 1 error. Now, you can find different mnemonics, but it is one of the harder things to try and keep those two straight. So here is kind of a grid that shows this. Now, here's something that we never know. We never know if the null hypothesis is true or if the alternate is true. But imagine that we can know that. So if the null hypothesis is really true, but we rejected it, then we committed a type 1 error. Okay, if the alternative is really true and we failed to reject the null, that's a type 2 error. Now, I mean, and the other two are, pretty straightforward. If the null is true and we failed to reject it, then that's exactly the result we want. If the alternative is true and we reject the null hypothesis, then that's also what we want. So those two are good. So yeah, we could substitute that in and we could see how that goes. All right. So here we go. Now we're turning this into probability again. So the probability of a type 1 error is the probability of rejecting the null hypothesis on the condition that the null is true. And there you go. Probability of type 2 error is probability of failing to reject the null hypothesis on the condition that the alternative hypothesis is true. All right, well, and I'll pause right there. Are there any questions on this idea? Pretty straightforward.
If we mess up, we don't get the check, like paradox, thing, you can't have the alternate be true. No, fail to reject.
Yeah. That's those two going together. That's a good thing. If the alternate is true and you reject, no, I'm with you. If the alternate is true and you fail to reject, that's bad.
Right.
Yeah, that's what you said. I misspoke. Okay, probability of a type 1 error is this, and this is what I already just threw out there. So let's figure out the actual probability of a type 1 error. Okay, we're going to do a little bit of logic. Hopefully we can handle this for just a short amount of time. We're going to have a hypothetical significance level of 0.05. I think we can stretch our minds to imagine this. So we want to, so let's imagine that we rejected the null because our p-value ended up less than 0.05. Actually, I don't like this real quick. I'm going to kind of describe it in a different way. Now, let's assume that the null is true because we're focused on this. The null is true. Now, we can get any result from this population. And we just happen to get a sample over here that put our average over here. And here's our significance level. So we chose to reject the null hypothesis. Now, what we don't know and what we can never know in reality is that the null is actually true. But our sample just happened to be one of those samples randomly drawn that caused us to reject the null. So are you guys with me on this so far? Okay, now, if our significance level is 0.05, then that means that there is a probability of a type 1 error that's equivalent to the significance level. Because 1 in 20 times, I'm going to get just a random sample of people that happens to be up at the high end, or if it was rejecting it on the low end. That can happen just by random chance. Does that make sense? The null is still true, but we happen to get this sample that can happen 1 in 20 times. And we got a statistically significant result that's actually inaccurate. And we ended up with a type 1 error. So luckily, this makes our calculation really easy. If you're ever asked, and there will be problems where they ask you for the probability of a type 1 error, in some way, shape, or form, they'll give that to you. It's always equal to your significance level. All right, so here is a comic to this effect. And I will just go through these slides really slowly. I'm going to pause recording for this. All right. So because of the types of problems that we just talked about, where you're going to get 5% of the time statistically significant results that aren't real. Well, that is potentially 5% of the time. there are some criticism of p-values. So some argue that only smaller p-values should be considered statistically significant, and that 1 in 20 is still too likely, right? So you want to have even more of a threshold. Maybe 1 in 100 of 0.01 is the correct alpha level. Now, this is not AP type stuff, but this is just understanding stats, because this is where it's going to intersect with your college career for most of you. I can almost guarantee you you're going to have a college project along the way where you're going to have to use statistics to justify your claims or something to that effect. And if you are ever running a true a study that you're going to be using statistics on, some ideas to make sure that you don't fall into this trap of just getting a random chance result. You can require hypotheses and significance levels to be announced before conducting the research, because what a lot of people will do is they will decide after they've run their analysis, they'll decide which significance level works, because they want to get a statistically significant result. So if you get a bunch of p-values and you decide, how about 0.03 is now my significance level, and then you can find like 2 results that work for you. But you need to decide this before you even have the data. And this is called p-hacking. And not just that, but there's lots of things you can do, like maybe throw out certain results because you decide that they weren't reliable. All right. Yeah, so yeah, you can mess with the data, you can clean data, and that is, and just as to continue this little brief tangent real quick, cleaning data, it's so nice in an AP stats class because they say, here's your data, do the analysis. Real stats, and I'm not a real statistician, I teach stats, right? But real statisticians have to clean data where they look at all the data and they have to figure out, okay, what data are we actually keeping? Because not all of this is good data. And that, I mean, I don't even know where to begin with that, but that is the real work of statistics. Okay. So there's also this idea where you have to duplicate the research. Let's say we go back to that comic. There's a link between green beans and acne, green jelly beans rather. So maybe you have to run that experiment again and make sure that you still get a statistically significant result. And if it's statistically significant a second time, it's unlikely that you're going to get a type 1 error 2 times in a row. Okay. And there have been replication studies that have thrown out a lot of previously statistically significant findings. Okay, and some of them are pretty well known. Not even though they're not coming to mind right now. There might have been some things that you've grown up hearing in your life because, oh, statistically this. Then you find out, oh, that was actually a flawed study. It wasn't a real result. So you might get some rude awakenings at some point in your life. So those of you who are doing research in the future, make sure that you're objectively analyzing data by establishing methodologies and rigorous criteria before you collect the data. You can still make mistakes, but it's unlikely to happen as often. And your professional reputation is on the line. Now, it's not like one strike and you're out unless it's shown that you were really, breaching some professional ethics and how you approach your research. But if it was like a mistake and you owned up to it, you said, oh, you know what, I made a mistake. It's not like you're going to be blackballed by your professional community. But I will say your reputation as a researcher, which you might not be a researcher in the lab, but a researcher in your career, in your job, your reputation will depend on if you are actually rigorous about collecting your data. Okay. So type 1 errors are generally worse in the academic world, but type 2 errors, failing to reject the null when you should have, might be worse depending on the situation. So here we go. You're researching if a particular chemical common in many foods is a carcinogen, specifically for colon cancer. Trying to be rigorous in your research, you're only going to accept results significant at the 0.01 level. When you compare the sample proportion of those who have colon cancer after ingesting large amounts of this chemical to the proportion of people in the population with colon cancer, you end up with a p-value of 0.0101. And of course, Objectively, you should fail to reject the null hypothesis. But now think about what a type 1 versus type 2 error is. Type 1, you reject the null when you shouldn't have. Type 2 is you fail to reject the null when you should have.
Wait, what?
I know that's confusing. That's a lot of words. No, I'm not saying that mockingly. I'm saying that's a lot to wrap your head around.
Fail to reject the null. You should have, that means you accepted the null.
Well, let's write down our
Whoa, dude.
What?
Well,
you never
Well,
say
like-
accept the null.
Well, like, okay. I'm brainstorming, spitballing. So technically that means you're accepting the null. Don't hit me, bro. Technically that means you're
it's more
accepting
like
it.
a brain drizzle.
And
It's more like a brain, like. sprinkle.
All right, I wrote down our hypotheses here. In this particular study, the null hypothesis is that there is no link between this chemical and colon cancer. The alternative is that there is a link. Now, let's say we make a mistake. If we reject the null hypothesis, but we're wrong, that's a type 1 error. If we fail to reject this one and we're wrong, that's a type 2 error. Which one seems worse?
Do you think we can go back to that one slide where we have the simple rows and columns?
Here, I'll do it this way. And we can also think through it this way. So null is rejected. So well, it's going to be tough for me to write that, isn't it? Okay, we can reject the null. I'll just say reject it, fail to reject. And this is what I was saying, and I'm not, I totally understand why this is confusing because you're trying to keep it straight. Like, wait, type 1, is that what I'm thinking of, or is that type 2? And failing to reject, yeah. So the null could be true. The alternative could be true. So if the null is true and we fail to reject it, that's good. If the alternative is true and we reject the null, that's good. But if the null is true and we reject it, that's type 1. If the alternative is true and we fail to reject it, that's type 2. And now maybe I want to ask this question. Imagine we make a type 1 error. We reject the null hypothesis and we shouldn't have. What's the consequence? Okay, so imagine in this scenario, the link between a chemical and colon cancer. In this scenario, we reject the null hypothesis. We say that there is a link when really there's not. What's the consequence? Yeah, what's the real world consequence here? Well, there would be some consequences.
People think that, something. They think it's not.
Yeah. And how does that affect people's behaviors maybe?
People try to stay away from chemicals because they think there's a link to colon cancer.
Yeah. People might avoid this chemical. The companies that use this chemical or produce this chemical, they're going to face some backlash and loss of profits. So we can say the consequences of a type 1 error, I'll just put T1 right here, is loss of profits or fear, public fear of this chemical, things like that. Those would be real world consequences, right? All right, now let's think of a type 2 error. So the consequences of a type 2 error This is where there really is a link, but we fail to reject the null. There is a link between this this chemical and colon cancer, but we say that there's not.
Like robot.
What's the consequences?
People are like, oh, colon cancer.
Yeah, more colon cancer, more deaths, more,
More people erupting.
yeah.
So that type 2 sounds worse. What's that?
So we have, so if we compare the consequences, this might be where as a professional, you have to make a decision, right? So the consequences of type 1 error versus type 2, we might decide, you know what? Type 2 consequences are more severe. I want to go ahead and err on the side of caution for public safety's sake. And I'm going to say that there is a link. Maybe I'm wrong, but we can determine that with more research. But I don't want to give people a false sense of security and say there's no link. All right. So I'm willing to make the type 1 error and have corporations be mad at me rather than type 2 and have people dying. All right. So this is where you get into some ethical problems. That's kind of fun, isn't it? Studying ethical problems in statistics in a math class. Okay, so now we found the probability of a type 1 error is just the same as the significance level. So the probability of a type 2 error, we're going to talk about that later, not today. All right, that one is not very straightforward. Let's just say that type 2 error probability is complicated. Okay, so let's wrap this up. Let me see. There's a lot of questions here. So let's talk about this just a little bit. If you are, and let me come back to this. So let me see. Sorry, I'm looking at something real quick to see if the question. I think we'll get into it with this problem. So I'm not going to take anything. Let's just jump into this question. The manager of fast food restaurants wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food. Now we're not talking about life or death, okay? So this is good. Based on store records, the proportion of customers who had to wait longer than 2 minutes was, there you go, the proportion is 63%. To reduce this proportion, the manager assigns an additional employee to drive-through orders. During the next month, the manager collects a random sample of 250 drive-through, finds P hat of 0.576, then perform their test with alpha at 0.10 significance level. And P represents the true proportion of drive-through customers who have to wait longer than 2 minutes to receive their food. So are we good with this scenario? Okay. Type 1 error, type 2 error. What does it mean in this situation? So I'm going to put type 1 right here. We can describe what the consequences are. Yeah, let me put it in Roman numerals, just keep it consistent. Type 2. Okay. So according to this, a type 1 error would be, just according in general, type 1 is we reject the null when we should not have.
So in this case, would the null be that there wasn't a change in customers when customers who had to wait longer than 2 minutes?
Yeah, the null is that there's no change and we rejected it incorrectly. So what are the consequences?
So we're saying that there is a significant result of not.
We are saying, yes, we're saying it was significant, statistically significant when it really wasn't.
You
And
were saying that there wasn't a change in the amount of people who had to wait longer than 2 minutes when there actually was.
yeah, and actually, yeah, I don't like how I phrase that. I mean, the result is statistically significant regardless, but it was just a random chance that we got a statistically significant result. In reality, there was no difference.
Oh yeah. Right. It's type 1 is you reject.
Yeah, we rejected the null. So in this case, we rejected this idea. So we're saying a change happened because of this extra worker.
So we made an extra worker work drive-through for no reason.
The consequence is extra worker. So it's an extra worker, which is extra costs. All right. I mean, we could come up with like all kind of small consequences, but that's the big one, right? We're paying an extra worker to sit there and it wasn't needed. So type 2 is we failed to reject the null when we should have. So we say that there is no difference when really there was. Now what's the consequence?
We are making customers wait longer.
Customers have to wait. All right. Customers have to wait longer because we failed to reject when we should have. So in this is not life and death, but between these two, which one seems like a more serious error? Making people wait longer. Okay.
That's
Next.
just a matter of opinion for the workers.
Hey, but if you're the worker and it gives you extra hours and more money,
Oh,
and you wouldn't have the shift otherwise.
And it's probably pretty easy to have to
Yeah.
well,
So-
I hated working drive-through.
But the big one, of course, is making customers wait longer, and that might drive business away if they don't want to wait for you. So you can argue your own case. This is not a cut and dry answer here, but this is a matter of opinion. Maybe you think it's type 1, maybe you think it's type 2. My guess is more people would say a type 2 is more serious here. Okay, so let's just, for argument's sake, say that type 2 is worse because we don't want to inconvenience our customers. And we can pay the extra costs because we'll get more orders that way. All right, now I'm not going to write that out, but there you go. So based on this, and we're going to, as a class, decide that a type 2 error is worse. Is the choice of an alpha level of an alpha level of 0.1 a good choice? And here's one thing I didn't talk about. And so this is where it's going to come up. Is as your, let me try and say this the right way. Type 1 error, right? This is equal to alpha. One thing that I didn't mention that now I need to mention for us to answer this, as your type 1 error increases, the probability of it, I should put it like this, the probability of your type 2 error decreases. So they are inversely related. So as one goes up, the other goes down. So knowing that we want to avoid, and we're deciding as a class, we're going to avoid this type of error, then do we want a higher or a lower significance level?
So they're inversely proportional.
Yeah, inversely related to each other.
So high.
We want a higher probability of type 1 because as type 1 goes up, type 2 probability goes down. So we might be happy with alpha of 0.10. Maybe we decide to raise it up even higher. Maybe we go to 0.15. So you can see a lot of this today is conceptual. And so you're asking a question, go ahead.
How would raising the significance value increase the chances of type 1?
The alpha level right here, the alpha level is equal to the probability of a type 1 error.
Oh.
Yeah.
Is that universal?
Yes, that's always true.
Oh, right. Yeah, you said that earlier. Sorry.
No, that's fine. It's a lot to try and wrap your head around. So type 1 is bad in its own way. Type 2 is bad in its own way. Which one's worse? If type 2 is worse, let's increase the odds of a type 1 error. And that therefore decreases the chances of a type 2 error. Okay. And the p-value. So maybe we're happy with the 0.10. Regardless, we have a p-value of 0.0385. And let's say we stuck with the alpha at 0.10. This is no different than what we did before. Because the p-value is less than the significance level, and here I can plug in the numbers, we reject the null hypothesis. There is convincing evidence that there is a decrease in waiting time by adding an extra employee. Okay. So that might be our conclusion here. We interpreted, or actually that's interpret the p-value. No, I didn't interpret the p-value. I just concluded it. So I gave you a wrong thing to say. The p-value itself is the probability that this result would have happened by random chance. So maybe what I would say instead is the probability of getting the results we got by chance alone, assuming the null hypothesis is true, is 0.0385. So there was only a 4% chance that this would have happened randomly. All right, I apologize for giving you the wrong interpretation at first, but are there questions on this? Okay. So I think what we will do is, I mean, we don't really have time to go through an entire problem, incorporating type 1, all this fun stuff. So I'm going to let you guys digest this a little bit. And actually, maybe this is a quick one we can answer, okay? So that we're not just doing nothing here. So environmentalists concerned about the impact of high frequency radio transmissions on birds found that there's no evidence of a higher mortality rate among hatchlings and nests near cell towers. They based this conclusion on a test using alpha 0.05. Would they have made the same decision at alpha equals 0.10? So first of all, did they, in the initial study, did they reject the null hypothesis or did they fail to reject it?
They failed to reject it.
They failed to reject the null. Okay, so if I create this, they failed to reject it.
So if you increase the alpha level, the chances that go down.
Yeah. All right. So in the first case, I mean, if the null is true and you fail to reject it, that's good. That's good. Type 1 and type 2. Now, okay, so they failed to reject it, and we don't really know if it's true or not, but this is the result they got. Let's assume that it's true and they failed to reject it. But if we increase the alpha level, are we more likely to reject it or fail to reject it? Using the same data.
More likely to fail to reject it.
Well, the higher your significance level means now there's, instead of a 1 in 20 chance that you're going to reject this by random chance, now there's a 1 in 10 chance you're going to reject it.
Oh.
So now we don't know what the actual numbers are. Would they have made the same decision? Maybe. We don't know what the p-value was, but they are more likely to reject it here at alpha equals 0.10. That's higher probability of rejecting. At 0.01, are they more, would they have made the same decision at 0.01 as they did at 0.05?
Probably.
Yeah. Yeah, because it didn't even meet the 0.05 level. 0.01 is more rigorous, so there's no way it would have been accepted at 0.01. So the probability of rejecting went down. All right. Hopefully you don't all have headaches trying to wrap your head around this today. It's not an easy thing. And it sounds childish, but I do encourage you to kind of think in terms of that boy who cried wolf, and then think about substituting the specific context into the problem. So you can remember, first of all, I rejected the null when I shouldn't have. That's a type 1 error. What is my null in this situation? And then what are the consequences as a result? It's a deep thinking process, and I'm going to call it good there. We will go through some more of this tomorrow. Okay. Take some Advil tonight. All right. Have a good one. I'll see you then.